On the 20th of July, 1969, Neil Armstrong stepped from a ladder onto the surface of the moon. He said something that everyone of a certain age can recite from memory. He planted a flag. He took photographs. He collected rocks. He returned to the lunar module. And he came home. The moon landing was, by any measure, one of the most extraordinary achievements in human history. A species that had been confined to a single planet for its entire existence reached out and touched another world. The distance between the Earth and the Moon, 384,000 kilometers of vacuum, was crossed by 3 human beings in a metal capsule running on technology that is, by modern standards, almost embarrassingly primitive.
Most people think they know this story.
The space race. America versus the Soviet Union. Kennedy's speech. Alan Shepard. John Glenn. Apollo 11. The flag. The moon. But almost everything that framing leaves out is more interesting than what it includes. The rocket that carried Apollo 11 to the moon was designed, in substantial part, by a man who had used slave labor to build rockets for Nazi Germany. The mathematics that made the mission possible was calculated by a group of black women whose names were unknown to the public for decades. The Soviet cosmonaut who beat the Americans to every milestone in the early space race was flying on a rocket whose lineage traced to a self-taught Russian schoolteacher who spent most of his life in a small town and died 32 years before the first satellite reached orbit. Space travel is one of the greatest achievements in the history of our species. It is also a story of exploitation, secrecy, competition, and the peculiar way that governments spend money when they are frightened enough. By the end of this, you will know the full story. Konstantin Eduardovich Tsiolkovsky was born in 1857 in the village of Izhevskoy in Russia, the 5th of 18 children. When he was 9 years old, he contracted scarlet fever and lost most of his hearing. The deafness isolated him from other children and from formal schooling. He educated himself, largely alone, from books. He was a strange and solitary child who grew into a strange and solitary adult. He worked as a schoolteacher in the provincial town of Kaluga for most of his life. He was largely ignored by the Russian scientific establishment. He built wind tunnels in his home. He conducted experiments on his own. He wrote papers and books that he published largely at his own expense. And in his mind, in the mind of a deaf schoolteacher in a provincial Russian town in the last decades of the 19th century, he worked out the mathematics of spaceflight. In 1903, Tsiolkovsky published a paper titled The Exploration of Cosmic Space by Means of Reaction Devices. It contained, among other things, what is now called the Tsiolkovsky rocket equation, the fundamental mathematical relationship governing rocket propulsion. The equation is this: the change in velocity a rocket can achieve depends on the exhaust velocity of the propellant and the ratio of the rocket's initial mass, including fuel, to its final mass after the fuel is expended. The higher the exhaust velocity and the higher the mass ratio, the greater the velocity change.
This seems technical.
Its implications are not. The rocket equation tells you exactly why spaceflight is so hard. Getting to orbit requires achieving a velocity of roughly 8 kilometers per second. The rocket equation, combined with the energy density of chemical propellants, means that the vast majority of the mass of any rocket must be propellant. A rocket that reaches orbit must consist of roughly 80 to 95% fuel by mass. The payload, the useful part, is a tiny fraction. Tsiolkovsky not only derived the equation, he proposed multi-stage rockets, vehicles that shed their empty fuel tanks during flight, progressively lightening themselves to improve efficiency. He proposed liquid hydrogen and liquid oxygen as propellants, the combination used in the Saturn V rocket that took Apollo to the Moon 66 years later. He wrote about space stations, about spacesuits, about the colonization of the solar system. He was the first person to work out the mathematics of how to leave the Earth. He died in 1935. He did not live to see Sputnik. Tsiolkovsky was not alone. In the early 20th century, several figures independently developed the theoretical and practical foundations of rocketry. Hermann Oberth was a Transylvanian-born German-Romanian physicist who, in 1923, published a book called Die Rakete zu den Planetenräumen, The Rocket into Planetary Space, which independently derived many of Tsiolkovsky's results and added important engineering analysis. Oberth's book sparked a wave of popular enthusiasm for rocketry in Germany and contributed to the founding of the Verein für Raumschifffahrt, the Society for Space Travel, in 1927. Robert Goddard was an American engineer who was, in practical terms, the most important figure in early rocketry. He launched the world's first liquid-fueled rocket in Auburn, Massachusetts, on March 16, 1926, a vehicle that flew for 2.5 seconds and reached an altitude of 12 meters. Not impressive by later standards, but an experimental proof of the principle. Goddard went on to develop pumps, gyroscopic stabilization, regenerative cooling, and many other technologies that became standard in all subsequent rocket development. He was awarded a total of 214 patents, many of them foundational. He worked largely alone in the New Mexico desert, funded by the Guggenheim Foundation. He was secretive to the point of paranoia, reluctant to share his results, and deeply suspicious that others would steal his work. He was right that they would. He was wrong that secrecy was the answer. In Germany, the Society for Space Travel's enthusiastic amateurs included a young man named Wernher von Braun, who joined in 1930 at the age of 18. Von Braun was brilliant, charming, and completely focused on a single goal: reaching space. He cared about rockets. He was, as he would later demonstrate, capable of considerable moral flexibility about the means by which rockets were built. Before we follow von Braun, let us follow the other line. In the Soviet Union, the legacy of Tsiolkovsky was carried forward by a series of engineers whose work laid the foundation for the Soviet space program, the program that, for most of the 1950s, was ahead of everyone. The central figure was Sergei Pavlovich Korolev. He was born in 1907 in Zhytomyr, in what is now Ukraine. He became an engineer, fell in love with rocketry in his early 20s, and began building experimental rockets with a small group of enthusiasts in Moscow. In 1938, he was arrested. Stalin's Great Terror was sweeping through Soviet society, and the purges were particularly devastating in technical fields, where accusations of sabotage and treason were easy to make and almost impossible to disprove. Korolev was accused of undermining the development of Soviet rocketry. He was tortured. He was sentenced to the Gulag, eventually to a mine in Kolyma, one of the most brutal camps in the Soviet system. He survived. His sentence was commuted. He was transferred to a sharashka, a prison. Design Bureau, a Soviet institution unique in its combination of forced labor and technical work, where imprisoned scientists and engineers continued their professional work while serving their sentences. After the war, Korolev was released, largely rehabilitated, and put in charge of the Soviet ballistic missile program. His identity was kept secret. He was referred to in public documents only as the chief designer. His name was not known outside the Soviet Union until after his death. It was Korolev who designed the R-7 rocket, the intercontinental ballistic missile that became the basis for all Soviet launch vehicles, and that, on October 4, 1957, carried Sputnik 1 into orbit. Korolev died in 1966 during routine surgery of previously undiagnosed cancer. He was 59 years old. Some Soviet colleagues believed that the years in the Gulag, the lost teeth from interrogation, the permanently damaged health, contributed to his early death. The man who designed the rocket that started the space race died without the world knowing his name. On October 4, 1957, a metal sphere 83 centimeters in diameter and weighing 83 kilograms was placed in orbit around the Earth. It transmitted a radio signal, a simple beep, that anyone with a shortwave radio could detect as it passed overhead. The reaction in the United States was not measured or philosophical. It was panic. The Soviet Union had demonstrated that it could put an object into space. That meant it could put an object, a nuclear warhead, anywhere on Earth. The Americans had believed they were ahead in the technological competition of the Cold War. Sputnik made clear, in the most public possible way, that they were not. President Eisenhower responded with what he publicly described as calm. Privately, the administration was alarmed. The National Aeronautics and Space Administration, NASA, was established in 1958. Funding for science and mathematics education increased dramatically. A space race that had in various ways been building for a decade suddenly became official, visible, and extremely expensive. The Soviets continued to lead. Yuri Gagarin became the first human in space on April 12, 1961. The first spacewalk was conducted by Soviet cosmonaut Alexei Leonov in March 1965. The Soviets had the first multi-person crew, the first woman in space, the first spacecraft to land on another planet. At every milestone in the early space race, the Soviets arrived first, and the Americans, watching each Soviet triumph, pushed harder. The rocket that carried American astronauts to the moon was called the Saturn V. It remains the most powerful rocket ever flown. It generated 34.5 million newtons of thrust at liftoff, the equivalent of 543 Boeing 747 engines firing simultaneously. It was designed by Wernher von Braun. Von Braun's story is one of the most morally complicated in the history of technology. He had joined the Nazi Party in 1937 and the SS in 1940. He held the rank of SS Sturmbannführer, the equivalent of a major. His primary contribution to the Nazi war effort was the V-2 rocket, the first ballistic missile used to bomb London and other Allied cities in 1944 and 1945. The V-2 was built at an underground facility called Mittelwerk, using slave labor from the Dora concentration camp. Between 12,000 and 20,000 prisoners, concentration camp inmates, including many who were too weak to work, worked to death or deliberately killed, died building von Braun's rockets. The V-2 killed roughly 5,000 civilians in the attacks on England. Von Braun was aware of the conditions at Mittelwerk. He visited the facility multiple times. The extent of his personal responsibility, beyond his role as the chief engineer of the program, has been debated for decades. What is not debated is that he knew what he was seeing and continued. At the war's end, von Braun and a group of his engineers surrendered to American forces, choosing America over the Soviet Union. They brought with them their technical knowledge, their designs, and the remaining V2 hardware. They were brought to the United States under Operation Paperclip, a classified program to recruit former Nazi scientists, suppressing or falsifying their wartime records to allow their immigration. Von Braun spent the rest of his career at the Army Ballistic Missile Agency and then at NASA. He became the public face of the American space program, telegenic, enthusiastic, a regular guest on television programs explaining the future of space exploration. He was awarded the National Medal of Science. He became an American citizen. He was beloved. The forced laborers who died building his rockets were not mentioned. This is the biography that NASA built its greatest achievement on. It is not a simple story, and it should not be told simply. On May 25, 1961, President John F. Kennedy addressed a joint session of Congress and made one of the most consequential single commitments in the history of American government. I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
The speech is famous.
What is less well remembered is the context. Kennedy had been president for 4 months. The Bay of Pigs, the CIA-organized invasion of Cuba that had failed catastrophically, had happened 3 weeks earlier. The Soviet Union had put Gagarin in space 3 weeks before that. Kennedy's administration was looking for a Cold War victory, and it was looking hard. The moon speech was not primarily a scientific aspiration. It was a geopolitical maneuver. The moon was chosen as the target specifically because it was far enough away that neither side was obviously ahead and close enough to be achievable within a decade. Kennedy himself, in a private meeting with NASA Administrator James Webb in 1962, recorded on tape and not publicly released for decades, was explicit. "I'm not that interested in space," he said. "I think it's important for political reasons, international political reasons. Is this important to science? Not particularly." He was concerned about Soviet dominance in space and its implications for American prestige and security. He was not primarily a space enthusiast. The program that he set in motion, the Apollo program, which would employ at its peak 400,000 people and cost, in today's dollars, approximately $150 billion, was the most expensive peacetime government program in American history. And it worked. In the early years of NASA, before the age of electronic computers, the calculations required for spaceflight were performed by hand. The people who did this work were called computers, a word we have encountered before in this series. At NASA's Langley Research Center in Virginia, a significant number of these human computers were black women. They worked in a segregated facility. They used segregated bathrooms, cafeterias, and work areas. They received lower pay than their white counterparts doing equivalent work. They were, in the institutional culture of the American South of the 1940s and 1950s, systematically disadvantaged at every level. And they did mathematics that sent human beings to space. Katherine Johnson was a mathematician who, in 1961, calculated the trajectory for Alan Shepard's flight, the first American in space. John Glenn, before his orbital flight in 1962, requested that Johnson personally verify the computer's calculations. He trusted her work more than the machines that were beginning to replace human computers. "If she says they're good," Glenn reportedly said, "then I'm ready to go." Johnson also performed the trajectory analysis for Apollo 11. Her calculations were fundamental to putting Armstrong and Aldrin on the moon. Dorothy Vaughan was the first black supervisor at NACA, NASA's predecessor, heading the group of black women computers at Langley. She recognized, before most of her colleagues, that electronic computers were going to replace human computers, and she taught herself Fortran, an early programming language, and taught it to the women in her group. She ensured their professional survival in a changing technological landscape. Mary Jackson was the first black female engineer at NASA. She had to petition a court for permission to attend the night courses at Hampton High School, a whites-only institution that were required for her professional advancement. These women's stories were largely unknown to the public until the publication of Margot Lee Shetterly's book Hidden Figures in 2016, and the film adaptation that followed. For decades, the history of NASA's computing work had been written without them. The moon landing was a collective achievement. The collection included people whose contributions were systematically obscured. On July 16, 1969, Apollo 11 lifted off from Kennedy Space Center in Florida. The Saturn V first stage generated its full thrust. The rocket cleared the launch tower. It climbed. It rolled. The first stage burned for 2.5 minutes and was jettisoned. The second stage burned. The third stage placed the spacecraft in Earth orbit. 4 days later, at 4:17 p.m. Eastern Time on July 20, 1969, the lunar module Eagle touched down in the Sea of Tranquility. Neil Armstrong called Houston. The famous words came, "The Eagle has landed." 6 hours and 39 minutes later, Armstrong opened the hatch, descended the ladder, and stepped onto the lunar surface. The line he had prepared, "One small step for a man, one giant leap for mankind," was transmitted back to Earth with a crackle of static. The word "a" was lost in transmission. It has been debated ever since whether he said man or a man, and whether the intended meaning came through. Buzz Aldrin followed him down the ladder and described the scene as magnificent desolation. They planted the flag, conducted experiments, collected samples, and returned to the lunar module. Michael Collins, the third astronaut, orbited above in the command module, alone in a way that very few human beings have ever been alone, on the far side of the moon, without radio contact with Earth or his crewmates. Armstrong and Aldrin returned safely. Apollo 11 splashed down in the Pacific Ocean on July 24, 1969. The mission was over. The decade was not yet out. Kennedy's promise had been kept. 5 more missions landed on the moon. Apollo 13 famously did not. An oxygen tank exploded mid-flight, and the crew survived only through a combination of extraordinary improvisation and the availability of the lunar module as a lifeboat. The last lunar landing, Apollo 17, took place in December 1972. No human being has been to the moon since. The Apollo program ended not because the technology had failed, but because the political will had. Kennedy's promise had been geopolitical. Once the promise was kept, once the Americans had reached the moon and the Soviets had not, the urgency dissipated. The costs of the program, which had been acceptable during the height of the space race, seemed harder to justify in the context of the Vietnam War, urban unrest, and the pressing domestic priorities of the early 1970s. NASA's budget peaked in 1966 at 4.4% of the federal budget. It has never exceeded 1% since. The Space Shuttle program, which replaced Apollo and ran from 1981 to 2011, was an extraordinary engineering achievement and a compromised one. The shuttle was the first reusable spacecraft, a genuine innovation. But the cost savings that had been promised never materialized. The vehicle was more expensive to fly than expected, more labor-intensive to maintain, and less reliable than the expendable rockets it was supposed to replace. 2 shuttles were lost. Challenger, in January 1986, broke apart 73 seconds after launch due to an O-ring failure in cold weather, a failure that engineers had warned about and been overruled on. Columbia, in February 2003, disintegrated on re-entry due to foam damage to the thermal protection system. 14 astronauts died in the 2 disasters. The International Space Station, the largest structure ever assembled in space, a collaboration between the United States, Russia, Europe, Japan, and Canada, has been continuously occupied since November 2000. It is a remarkable achievement of international cooperation between countries that were bitter rivals a generation earlier. The commercial space era began in the 2000s, with SpaceX demonstrating that private companies could develop orbital rockets and, eventually, reusable ones. The Falcon 9's reusable first stage, landing itself after delivering a payload to orbit, was a demonstration that changed the economics of spaceflight in ways that governments had struggled to achieve for decades. As of now, 67 years after Sputnik, 12 human beings have walked on the moon. All of them were American. All of them were male. The most recent was in 1972. Robotic spacecraft have visited every planet in the solar system. Voyager 1, launched in 1977, is now more than 23 billion kilometers from Earth, the most distant human-made object in history, operating in interstellar space, still transmitting data. Mars has been orbited, landed on, and driven across by rovers. The Perseverance rover, currently operating on Mars, is collecting soil samples intended for eventual return to Earth. The Ingenuity helicopter, which traveled with Perseverance, demonstrated powered flight in a planetary atmosphere other than Earth's, the first such flight in history. The James Webb Space Telescope, deployed in 2021, is observing galaxies formed less than 1 billion years after the Big Bang. Looking back in time, 13 billion years, seeing light that left its source before the Earth existed. The next lunar landings, planned under the Artemis program, will, for the first time, include a woman on the lunar surface. The first person of color on the moon is planned for one of the early Artemis missions. A return to the moon, and eventually missions to Mars, are being planned by multiple nations and multiple private companies. The timeline is uncertain. The motivation is a mixture of scientific curiosity, national prestige, commercial opportunity, and the oldest and most persistent of human drives: the need to go beyond whatever edge is currently visible. We live on one planet. We are, as far as we know, the only species in the history of the universe that has left the world it evolved on and traveled to another. That fact, the strangeness and the wonder of it, can sometimes get lost in the political calculations and the budget battles and the arguments about who gets credit.
It should not get lost.
There is an equation written in a small museum in Kaluga, Russia. It is the Tsiolkovsky rocket equation. The fundamental relationship between exhaust velocity, mass ratio, and achievable velocity. The mathematics that tells you what it takes to leave a planet. It was derived by a deaf schoolteacher in a provincial Russian town, working alone from first principles in 1903. He did not live to see it used. He died 2 years before the first artificial satellite, the satellite that his equation had made possible, reached orbit. His grave is in Kaluga. The museum near his home contains models of the rockets he imagined and the spacecraft he described, all of them built using the mathematics he worked out alone. The Saturn V that carried Apollo 11 used the Tsiolkovsky equation. Every rocket that has ever reached orbit has used the Tsiolkovsky equation. Every probe that has visited another planet has used the Tsiolkovsky equation.
The moon landing was real.
The rocket equation is real. The hidden figures who calculated the trajectories were real. The slave labor that built the V2 was real. The cosmonaut, whose name the world did not know, was real. The schoolteacher, who worked out the mathematics in a small Russian town, was real. Space travel belongs to all of them. It belongs to the mathematicians and the engineers and the test pilots and the politicians and the funders and the dreamers. It belongs to the people history remembered and the people it forgot. It belongs to Tsiolkovsky, who derived the equation, and Korolev, who built the rocket, and Katherine Johnson, who calculated the trajectory, and Armstrong, who flew the mission, and the 12,000 prisoners who died building the machine that the Americans learned from. The next step, whatever it is, whenever it comes, will belong to people we have not yet met. And the equation that makes it possible is already written on a wall in Kaluga.